So our base here was 1/2, and our height we chose is the y coordinate 1, so f of 1. Plus our rectangle number 2, this one, our base is again 1/2. Times this time between we were looking between 1.5 and 1, and so we're choosing the leftmost endpoint. So we're choosing the y coordinate at 1.5, f of 3/2. Plus our base is still 1/2 times this one between 2 and 2.5. This time we're using 2 since that's the leftmost. Plus our base is 1/2, and then our height of the last one is going to be f of 2.5. So that's 5/2. And one thing that's going to make it easier if you're needing to add these up by hand, especially if they're equal subintervals, if they're all the same subinterval, that means they all have a base of 1/2. So I can take a 1/2 and factor it out of here. Plus f of 2 plus f of 5/2. So we can calculate what each of these are. F of 1, 16 minus 1 is 15. Plus f of 3/2 here, 3/2, that'll be 16 minus 3/2 squared is going to be 9/4. And so that is 64/4 minus 5/4 is going to be 55/4. Plus f of 2, well, that's 16. That's 16 minus 2 squared is 4. So that's going to be 12. Plus f of 5/2. Now we're subtracting 25/4. So 64 minus a 25, that's going to be 39/4. (15) and 12 is 27, which is going to be 108/4. So that's these two put together. And then 55/4 and 39/4, that's going to be 55 and 39. That's going to be 94. (108) and 94 is going to be 202/4. And so however you want to do that, I would say the easiest is these cancel. So we get 101/4 as our approximation. So again, this is the guess for what the actual area is. Now, we will eventually have a method for knowing what the exact answer is. But this is a way of getting an approximation. This is a way of getting a guess. And the thinner our rectangles are, the better our guess is going to be. So that's the idea behind this one. If you're curious, Again, we're approximating an answer here. If you're curious, the actual answer is going to be 70/3. And later on this week, we'll talk about how to do this. This is going to be a fairly straightforward process for how to get the actual exact answer. Again, this is giving an approximation for that. And so you'll notice this is a little more than 25 because that would be 100/4. This is a little more than 23. This is 23 1/3. So this is an overestimate of the actual answer, right? This is a larger number than the actual answer turns out to be. And hopefully that makes sense to you because in each of these rectangles, we have this little sliver of area happening on these rectangles. And so that's creating a larger area than is actually in the answer. If you look at how the right Riemann sum was drawn, that answer, that final answer, would give an underestimate of the actual answer. Because it'd be the opposite. There'd be some area that was in the curve that we wanted that isn't actually covered there. So that's left Riemann sum and right Riemann sum. The easy way to get the easier way to remember which points you're going to use because of how you're choosing the points for LRAM. We're going to pick them all except the far right. In other words, because we're always choosing the one on the left, the very rightmost endpoint didn't get chosen, didn't get used. And it's going to be the opposite for RRAM. When you're doing RRAM, you should choose them all except the far left of the interval. So all of them except for the leftmost endpoint of the interval. And that will that'll be a good rule of thumb for knowing which points to pick. So when we did LRAM, we picked 1, 1.5, 2, 2.5, but not 3, not the rightmost endpoint. When we did RRAM, we didn't pick 1. We started at 1.5 because we didn't want that leftmost endpoint. And then we went 1.5, 2, 2.5, 3. Now, there is another type of Riemann sum, type of way to draw these rectangles that can give an even better approximation. And the way that we can do that is to use I said we come back to this, the midpoint to find the height of the rectangle. Because remember how the overestimate and underestimate got created? Well, if we split the difference and use the midpoint, well, a lot of that over and underestimate is not going to happen anymore. Midpoint of each of those to plug into F. But it's often a more accurate approximation of the area. So midpoint Riemann sum is usually going to be a better choice, but it's usually a harder thing to actually evaluate. And so I'll give a visual of what that looks like, but I won't go through the calculation because it can often get to be a more complicated calculation. So let's take a look at what that looks like for the one that we just did. And then we'll do a couple more examples with it as we go through today. All right, so I'm drawing the same curve that I drew before. We're still going from 1 to 3, but this time we're going to use a midpoint sum. So here is 1, here is 2, here, well, let's do that again. That was not spaced out evenly, so I wasn't happy with it. So let me split this up better. Here is 4. 2 needs to be halfway from there. 1 needs to be halfway there. Okay, so here's 1, here's 2, here's 3. And the area that we're trying to find is from 1 out to 3. So area of the rectangle, base times height. The bases, we're still using 4 rectangles. And so we're still using 1/2 as our base. But this time, when we look at what to make our height, we're gonna need more than splitting in halves. And by the way, just like left was used for LRAM, R was used for RRAM and right endpoint, midpoint is going to be MRAM. So 4. So we are still going to go from 1 to 1.5, from 1.5 to 2, from 2 to 2.5, from 2.5 to 3. We're still going to do it that way. The difference is that to get our height, we're going to use the midpoint. And so, for example, to take the first rectangle from 1 to 1.5, which one are we going to use? The 1 or the 1.5? Well, we're going to use neither of them. We're going to split the difference and go halfway in between 1 and 1.5. And we're going to use the height at 1.25. So I'll go ahead and at the start, since all my bases are 2, I'm going to go ahead and factor the 1/2 out to start with. But this time, my first rectangle is going to use the height at 1.25, like this. So we're going to use f of 5/4, 1.25. Our second one, the base is still 1/2. That's why I factored the 1/2 out. But then for 1.5 to 2, instead of using 1.5 or 2, we're going to split the difference and find halfway in between. Right? MRAM, we're using the midpoint. So we're using f of, instead of 1.5 or 2, we're using 1.75. And then between 2 and 2.5, we're going to split the difference and use the height at 2.25. Base is still 1/2, so the 1/2 can still be factored out. 2.25 is 9/4. And then we're going to use f of 11/4. Again, halfway in between 2.5 and 3. So then we would find these values. F of 5/4, for example, that means we want 25 over 16, which means that now we're dealing in 256 over 16 minus 25 over 16. Like plugging in 5/4 and 7/4. This is a lot more complicated. You wouldn't have to do this by hand most likely, so I'm not going to. But this is going to get an answer that is even closer to our actual answer than we had before. Okay, so hopefully we're able to get the graph and plot those points onto the graph. Remember, we're only focused on from 10 to 70. And now we want to start to build our rectangles on this one. If we're building these rectangles, and I want to go from 10 to 70, the key part of what might be tripping you up about this is that you might think, oh, we want to go from 10 to 20, from 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70. So that would give me 1, 2, 3, 4, 5, 6 rectangles. But we're only supposed to have 3 rectangles. So that means we need to narrow things down a little bit. And instead of putting our rectangles in increments of 10, we want half the number of rectangles. So we need to go twice as far. So our first rectangle is going to go from 20 to 30. And then we're going to build a rectangle that goes from 30 to 50. And then we're going to build a rectangle that goes from 50 to 70. And that will give us 3 rectangles. So from 10 to 30, from 30 to 50, from 50 to 70. So rectangle number 1 is going to go from 10 out to 30. And so our base is going to be 20. Distance from 10 to 30. In fact, all of the bases are going to be 20. So when we go in the formula, I'll be able to take a 20 out of the whole thing. And then our height for rectangle number 1, since we want to use a midpoint Riemann sum, we want to use the midpoint as a height. So halfway between 10 and 30, which would be 20. So V of 20 is what we're going to use as our height for the first one, which is 22. So 20 times V of 20. And the rectangle is going to look like, well, here's 10, here's 30. So we want halfway. We want to use this as our height. There's what the rectangle looks like. Plus, I'll do the other ones faster. Rectangle number 2. We still want our base to be 20, the distance from 30 to 50. But for rectangle number 2, what is halfway between 30 and 50? Well, 40. So that y value is what we want to use for splitting the difference and building as our height. So there is rectangle number 2. So our base is still 20. And then our height is V of 20. Or sorry, V of 40. Halfway between 30 and 50 now. And then plus our last rectangle, this time it's going to go from 50 to 70. So we're going to use 60 as our height. 20 still our base. 20 still our base. And we're using the y value at 60, halfway in between 50 and 70 to build our height. So now I'll go ahead and factor 20 out. And we'll go ahead and write these down. Let's see. 22 plus 35 plus 44. If I add all those up, that's going to give me 101, I believe. 10, 10, so 20, 20. The units here, we were given v of t. If I were taking the derivative, I would get acceleration. But the antiderivative here, which is what we're approximating, working backwards, remember, is position. So our answer here ends up being about position. Miles. So we're using our velocity to accumulate position. So the 20 miles, this is going to end up being the distance, or sorry, not miles. This is in feet. Feet. So the 20 feet is the distance traveled from t equals 10 to t equals 70. So that is what the answer means. If you didn't get that exact interpretation, don't worry about that too much. We will talk about that a lot more as the chapter goes on. The key thing you should be able to get right now is that because we're working backwards, that we started with velocity, so working backwards would get us to position. And so knowing that working backwards, we want to look at position, so our label is going to be feet instead of feet per second.